Welcome back. In this important lecture, we will relate how mass is connected to energy and reduction in mass gives rise to the binding energy of a nucleus. Einstein's theory of relativity showed this relationship. An object with a mass m has an energy content equal to mc squared, where c is the speed of light. We are not going to derive this relationship or elaborate any further, but this relationship is going to be utilized to discuss binding energy observed in nucleus. So let's try to understand how to use this relationship to look at the binding energy of nucleus. For example, in a previous lecture, we had mentioned that an isolated neutron is unstable and beta decays to proton. So with this statement and with this relationship, you should think, how do you connect these two observations and relationship? So what can be inferred about the mass of neutron, proton, and electron? Pause for a moment and then answer this for yourself. So from all these things, when you put them together, you can say that the mass of the neutron is greater than the combined mass of proton and electron, because this is unstable and decays to these products. So let's look at the numbers. So mass of proton is this much atomic mass unit. Mass of neutron is 1.00 this much atomic mass unit. So you can see that the neutron mass is greater than the proton mass. And you know what is the mass of electron with respect to proton, right? One more question that you may want to ask is, you would have thought that mass of hydrogen would be one atomic mass unit, right? That's not so. It is something more than one. So what exactly, why do we need this? Okay, on what basis do we have this atomic mass unit? So to answer this, you have to first understand that the mass of carbon 12, that is carbon with 6 protons and 6 neutrons, that has a mass of 12 atomic mass unit. Okay, so this is an integer. Therefore, the nucleons in carbon, there are 12 nucleons. So each of the nucleon, we can we will look at how to think about the so-called mass defect and the binding energy in the next thing. But what is important to understand is this atomic mass unit came via defining the mass of C12, carbon 12. All right, so what is the binding energy of nucleus? Binding energy of a nucleus containing Z protons and A minus Z neutrons is given by this formula. How do we think about this? This is like a chemical reaction, right? So imagine that you have Z number of protons isolated from each other and A minus Z number of neutrons isolated from each other. They are all brought together to form a nucleus with atomic number A and atomic weight Z, right? So when you do that, because there is an energy equivalent for mass, with this formula, you can write the binding energy of the nucleus. Let's implement this in some cases to understand it better. What is important to understand is, because nucleus is stable, the mass of nucleus is less than the combined mass of independent nucleons, right? So when they're all separated, and then you add that mass, and when all these nucleons are present inside the nucleus, the combined mass is lesser, and this reduction in mass is the reason for the binding energy of nucleus, right? So when you reduce mass, things become more stable. Reduce energy, things become more stable. For example, when you have helium, you have 2 protons and 2 neutrons. And you know the mass of isolated proton, mass of isolated neutrons, when they're combined together, and you can measure the mass of helium. When helium nucleus is so formed, there's a mass reduction of this much amount. This mass reduction is called mass defect. Actually, the greater this quantity, the greater the mass defect, more stable is the nucleus. In the context of helium, the energy equivalent of this mass defect is this number. So this is the typical unit we use for discussing the energy of nuclear processes. Okay, so this mass combined with c squared will give rise to this particular binding energy. This energy is liberated and leads to the binding energy. Greater the binding energy, greater is the stability. So in this case, this liberated energy is a source of heat and light in the sun. This is the reaction that is hypothesized and to occur in the sun. There's a lot of experiment evidence for that too. So in a way, sun is generating a lot of heat and light. That's because it is also losing lot of mass every second. This number appears to be large, but because sun's overall mass is very, very large, this is a tiny fraction of the mass of the sun. The mass lost per second is a small fraction of the overall mass of the sun. So this is an important concept that you should internalize. So overall, it's better to think through energy than through masses. Okay, so here, even though we are using the same symbol B, but here in the y-axis, it is binding energy per nucleon, not the overall binding energy. That is what is plotted in the y-axis. Along the x-axis, we are plotting the mass number A, all right? What do we see? The binding energy gradually increases over a particular mass number. The binding energy is approximately constant compared to the overall scale. Okay, so there is this region, and then the binding energy per nucleon decreases, right? So that is the observed behavior. So whenever there is an extrema, like in this case, there's a maxima, right? Even if there's a minima, the same, what I'm going to say is true. So whenever there is an extrema, it is because of 2 competing factors, okay? So which are varying in the opposite manner. That is, there is a factor which is supposed to increase as you increase the mass number, and there's another factor which is going to be constantly decreasing as you increase the mass number. So the intersection of both these things give rise to a maximum. So in this case, what are these 2 features? So Coulomb repulsion, there's always a repulsive interaction. This increases as z squared, right? So that keeps on increasing. And there is an attractive interaction because of strong nuclear forces that increases linearly with z, okay? So that is the reason why you have a maxima. Okay, so this constantly increases and this constantly decreases. So when Z is smaller, uh, this tends to dominate. When Z is larger, because this varies quadratically with Z, this dominates. So the reason why the binding energy decreases as the mass number increases in this region is because uh, the effect of Coulombic repulsion is much larger. So that Coulombic repulsion dominates here, the binding energy decreases. In this case, the reason why attractive interaction increases in this region, this is the dominant effect. Slightly more complex because this is because of strong nuclear forces, which is very short ranged. This is more long ranged than this. So this aspect we will elaborate later, but the important thing to understand is whenever there is a maxima, you can decompose uh, the effect into two different effects, and yeah, so and the two different effects here are this effect and this effect. So there is a better schematic which gives you more details. So the average binding energy per nucleon is highest for iron 56 in a sense that this is the nucleus which is most stable. Here, these are all not very stable. The stability keeps increasing because the binding energy per nucleon increases, and there is a flat region wherein many elements have approximately similar binding energy per nucleon, and then it decreases gradually. So in the next lecture, we will look at some other feature of nucleus that is to do with the nuclear radius and density. Thank you.